All right. Well, thank you for having me. It's a pleasure for me to do this. So I'm going to tell you about the James Webb Space Telescope. We are about to launch it, and so I have some slides. I'm going to get through them. If you have any questions, please stop me. But I'm gonna try to get through them and leave plenty of time for questions. But perfectly happy to be interrupted and answer any questions. Um, I'll talk about the case for Webb, the unanswered science questions it's going to try to address, why it's the tool for the job, and I'll talk a lot about the designing, building, and testing of it, and then finally using it and the expectations. So I think you all know that telescopes are certainly powerful tools of exploration. The universe is ridiculously vast compared to our notions of space and time. I like to use the 1/10 billionth scale model of the universe, especially when I'm talking to people not as knowledgeable as you, to try to illustrate just how vast the universe is and how slow the speed of light is when you think in our concept of things. So at the 1/10 billionth scale, the sun is about the size of a grapefruit. The Earth is about the size of a ice cream sprinkle, and it's 15 meters away. The moon is about the size of a grain of salt or a poppy seed from a poppy seed bagel, and it's about 1.25 inches away from the Earth. And the speed of light at this scale is 3 centimeters. So that's about how fast one of those black carpenter ants can crawl. It takes 15 minutes for the ant to get from the grapefruit to the Earth, the ice cream sprinkle Earth. And the next nearest star is, of course, almost 4 light years away, which makes it if you're near Washington, D.C., like I am, I'm just outside Annapolis, Maryland right now. The next nearest star is a walnut in Seattle. It takes the ant almost 4 years to get there. And Sirius is a volleyball in Lagos, Nigeria. And of course, it takes about 9 years for the ant to get there. Also at this scale, Voyager 1, which is the farthest thing that we've sent into space, is only a little over 2 kilometers away. And if it were headed towards the next nearest star, which it's not, but if it were heading that direction, it would take it about 86,000 years to get there. So obviously, the universe is large compared to our notions of space and time. And it's also a good argument for taking care of our own planet, because we're not going anywhere else anytime soon. But telescopes can probe far, far beyond where we can go ourselves or send our robots. And as this group is probably well aware, there's imagery and spectroscopy, and imagery tells us structure, and spectroscopy tells us composition and speed. So those are the two broadest kinds of instruments. So Webb is primarily an infrared telescope, and it's really trying to address, there are 4 general science themes, but in general, they're kind of 2 things. Originally, Webb was envisioned to probe the end of the cosmic dark ages. How did the lights turn on in the universe, basically? The first luminous objects that formed in the universe emitted ultraviolet and visible light, but they formed only a few 100 million years after the Big Bang. So when the universe was only a few percent its current age of 13.8 billion years. And of course, this light has been redshifted by cosmic expansion since the Big Bang, and it reaches us here and now as infrared light. So to see the very first ultraviolet and visible light emitted by the first luminous objects in the universe, you actually need an infrared telescope today to see it. And this is an old question that even before Hubble was launched in 1990, scientists realized it probably couldn't answer, because it's too small and it's too warm. It is primarily an ultraviolet and visible telescope with a little bit of near infrared capability. And it's 2.4 meters in aperture, even though it has an exquisite point spread function and it's above the atmosphere. it's just too small and too warm to answer this question. What's needed to explore the epoch of the very first stars and galaxies, you need a very, very large, very sensitive infrared telescope, and that means it needs to be in space to have the required sensitivity. Now, something else that has come along since this original reason for Webb as the next logical step as a large observatory in space is, well, what are exoplanets like, and could any be habitable? And of course, back in the late 80s and early 90s, when people were thinking about Webb and to follow Hubble, exoplanets weren't really even a thing. But that's a tremendously exciting new area of science, is exoplanets and astrobiology. And exoplanets being relatively cool things, they're brightest in the infrared. The processes of their formation are cool and they're bright in the infrared. And those processes are typically shrouded in dust, which scatters visible light, but infrared light can much more easily penetrate. And oh, by the way, many spectral fingerprints, the absorption and emission lines that are unique to every element and molecule and identify them. Those a lot of the real interesting features of spectra are found in the infrared. So an infrared telescope is just an ideal tool for studying exoplanets nearby. When I mean nearby, of course, in stars that are in our local area of the galaxy. So, parsecs away, not, many light years away. But and there are certainly a lot of interesting targets that have been identified by other missions like Kepler and TESS, and that Webb will go explore. So a very big, very sensitive infrared telescope in space is great for answering a whole range of questions, old ones and new ones. Just sort of a diagram of the timeline of the universe. It began with the Big Bang about 13.8 billion years ago. In the first, fractions of a second, there was inflation where things expanded at superluminal speed. The laws of physics that as we understand them in the states of things as we live in them didn't apply. But the cosmos kind of grew to cosmic scale in a fraction of a second, and but it was a plasma until about 300 to 400,000 years after the Big Bang. Things cooled off enough that ordinary matter, which was only hydrogen and helium and trace amounts of a few other things, those protons and neutrons and helium nuclei, things cooled off enough for that helium and hydrogen and helium to combine. It's called recombination. I've never understood that, why astronomers call it recombination, because it was combination. But around 400,000 years ago, that things cooled off enough, and the neutral hydrogen and helium, formed from the plasma, and then light was free to propagate. But then we have the cosmic dark ages, somewhere in the first few 100 million years. So, and then there's a tremendous amount of activity that ended it with the first stars, the first galaxies. So how did that happen? What came first? Stars, galaxies, black holes? How did supermassive black holes that we see at the hearts of galaxies today, how did they form? And I'm not a scientist, but these are the big, I'm an engineer, these are the big science questions that people have. Webb is designed to actually probe the end of the cosmic dark ages and directly observe what happened, and actually image the very first galaxies that turned lights on in the universe. So, and then today, in more recent cosmic times, we've seen that the expansion rate of the universe is actually accelerating. Webb may be able to help answer some of that, but it's really to understand the end of the cosmic dark ages and then examine galaxies throughout the history of the universe and understand their formation and evolution and how did the universe get to look like the way it is, and maybe figure out where it's going. And of course, there's some really cool exoplanet stuff that just by good fortune, Webb is a really excellent tool to probe that. So now I'll talk a little bit about its characteristics, the engineering of Webb. So this is an image of what it will look like in its deployed operational state in space. Doesn't really look like my 10-inch Dobsonian. Doesn't look like Hubble. So why? So, well, first of all, it's got to be large for resolution and sensitivity. The aperture, we know we needed a way back in the day. We knew we needed a large filled aperture. We know we need something at least 6 or 7 meters in diameter, and this is about 6.5 meters in diameter. We need that for the sensitivity to do the science I described, and it'll give us the resolution we need to. The optics are cold, and the instruments are cold for infrared sensitivity. So, as many of you know, infrared light is heat radiation, and to have a really sensitive infrared telescope, you don't want it to be seeing its own thermal emission. You want it cold. And of course, infrared, the best infrared detectors, the ones we need, they basically need to be cold to work, to detect infrared photons. So everything on, if you can see my cursor, everything on this upper half of the slide where the telescope optics are and the instruments behind the primary mirror are anywhere from, they'll passively cool from anywhere from the mid-20s to the mid-50s Kelvin. The mercury cadmium telluride detectors in the 3 near-infrared instruments are all passively cooled to 37 Kelvin, which is kind of a sweet spot for a compromise between high quantum efficiency and low noise performance. And there's one instrument that uses arsenic doped silicon detectors to see mid-infrared wavelengths, and those detectors need to be colder than 7 Kelvin, which we can't really get to passively because the effective sink temperature of space from the vantage point where this telescope is going is about 7 Kelvin itself. So we actually have a refrigerator, a cryocooler, that will cool the detectors for that mid-infrared instrument down to below 7 Kelvin. So it's big and it's cold for the sensitivity and the resolution that we need. One of the iconic features of this observatory is this big 5-layer kite-shaped sun shield. And there's no tube around the optics, and that sun shield provides shade for the telescope and the instruments and enables them to cool passively. And by passively, I mean you put something in the shade in our solar system, and it will get cold pretty fast. And not putting a tube around the telescope, because the sun shield does most of the baffling, and we're concerned about infrared stray light, really. Not having a tube actually is important so that this thing can radiate its heat and passively cool. Now, of course, this thing is really large. It's about the area of a tennis court, and it's more than 3 stories tall in this deployed state. That doesn't fit on a rocket like this, nor would it survive launch in this deployed condition. So it's really a giant origami observatory. We had to design it to be folded up for launch and then unfold by command in space to this operational configuration. And we had to design it to be folded anyway because 6.5 meters for an aperture is bigger than commercially available 5-meter rocket fairings. And furthermore, the primary mirror, by making it segmented so we can fold it, also allows us to make it very lightweight. If we use the same very lightweight monolithic glass mirror technology that Hubble's primary mirror has, this would be almost an order of magnitude more massive, and it would require a correspondingly massive support structure that could survive launch. So it's just a compounding problem. But by building this as a segmented mirror, which of course we'll have to align when we get into orbit, we can fold it very compactly for launch and then unfold it in space. And then we're sending it to a location away from the Earth. The Earth is a big room temperature object, so we need to get away from it so that Webb can get to its cold temperature for sensitivity. So we're going to the Sun-Earth Lagrange point number 2, which is actually relatively easy to get to. It's easier to get to than going up and down, up the Earth's gravity well and down the moon's gravity well and landing on the moon. And there's other problems with having a telescope on the moon, like cleanliness, and moon goes around the Earth once a month and all sorts of things like that. It's actually easier to build a big space telescope and stick it in space. And going to Lagrange point 2 is kind of the Goldilocks location. It's relatively easy to get to, doesn't take a whole lot of energy with a rocket. It's not so far away that it's difficult for communications, high bandwidth communications, and but it's a great place to put a telescope like this, where it can get cold, and you can just keep the optical side of the observatory facing deep space all the time, and keep the sun and the moon and the Earth on this side of the observatory, and you've got a perpetually illuminated solar array to generate power. So it's a great place to put a telescope like this. So that's the general characteristics. So what makes it hard? Well, an engineer friend of mine once said this years ago, that a piece of cake turns into a brick at 40 Kelvin. And it's the truth. Things get weird when they get really, really cold. As I mentioned, Webb has to be cold so it can detect faint infrared signals rather than seeing itself. We're running colder than 60 Kelvin so that we can be, our background limit is actually the zodiacal light. It's actually scattered and re-emitted infrared light from dust, diffuse dust that's in the inner solar system. L2 is about 1 million miles away in the anti-sun direction, so in the midnight sky. And we're orbiting that point. And in an orbit that's actually bigger than the moon's orbit is around us. We're in this 6-month loop going around L2. And being out there, we can get pretty cold. But so when you combine the sensitivity of our detectors, the low thermal background of our optics, the incredible sensitivity and low dark current of the detectors in the instruments, and the really low noise performance of the electronics that read out those detectors and process the signals, all of that noise added up is less than the zodiacal background. And by being under 60 Kelvin and having all these wonderful detectors and electronics, we're limited by the environment we're flying in. We're not limited by the machine itself in terms of sensitivity. Something else that being cold makes this hard is, we built this thing at room temperature, but it operates at cryo temperature. So we actually had to build it perfectly wrong so that it's exactly correct at its operating condition. As most people know, typically materials expand with warmth, they contract with cold. Different materials change dimensions differently with temperature. They have different coefficients of thermal expansion, it's called. By necessity, we had to build Webb out of many different materials. And the mirrors especially and the structures that hold them, they all have to be the right size and shape when cold. So that was a really hard problem. And that's part of why it took so long to build this thing. And that leads right into testing. Testing was extremely difficult due to size and temperature. So deployment testing of something this large, designed to work in 0G and deploy in 0G, but tested on the ground, required a lot of big offloading equipment and a lot of care. Much of the testing of the hardware had to be done in vacuum chambers, and for the cold parts, 2/3 of this 6-ton observatory, it only weighs 6 tons. It's like many times bigger than Hubble, but it's half the mass. This 2/3 of the mass of the 6-ton observatory, we had to test it in cryogenic temperatures in vacuum chambers, and testing everything all at once in one piece in a vacuum with hot sun on one side and excruciating cold on the other wasn't feasible on the ground. So we actually had to test it in 2 main halves and combine results from different tests and to generate the objective evidence that this thing works and will work in space. So a piece of cake really does turn into a brick at 40 Kelvin. So the Origami Observatory I mentioned is too large to fit in a rocket or survive launch without folding it up. Here you see the stowed condition for launch atop an Ariane 5 rocket, and this is what it looks like deployed for operations. So here's a little video to illustrate this, the stowing. We're flying on an Ariane rocket because Canada and Europe are partners with us, with NASA, in this endeavor. And one of the contributions of Europe is the launch vehicle and the launch services. They also are providing 2 of the 4 instruments on the telescopes that are big partners with us. So this is what Webb looks like. And we're about to do this operation. This is coming up in a few weeks. Putting this atop the rocket. We're actually down in French Guiana now, and I'll talk more about that in a bit. And if we look at deployment, so we have a 26-minute rocket ride on an Ariane 5. It'll send us to escape trajectory to L2. Actually, it'll send us in a really, really highly elliptical orbit, but fuel on board we use to do a mid-course correction and shortly after launch, and that will put us into an orbit around L2. But so it's almost escape velocity. We'll be going almost 10 kilometers a second when we get off the rocket after 26 minutes of powered flight. So this is what we look like stowed and having just separated. So if I hit play here, this is the observatory stowed. First thing that comes out is a solar array, which is the one automatic deployment that we have. Everything else gets deployed by command. This is the high gain antenna coming out. Now you're seeing the 2 big pallets, we call them, that hold the 5 layers of Z-folded sunshield membrane. Then the telescope and the spacecraft bus separate for thermal and mechanical isolation, and this also allows for the sunshield to start unzipping, which you're seeing here. Some covers retract. Then these telescoping composite mid-booms start to extend one side and then the other. They'll pull the membranes out with them. And oh, by the way, there are 107 little retractable pins actuated by non-explosive release devices that pin the membranes down for launch so that they're controlled. Now the 5 layers get separated and tensioned so that this thing acts as a very efficient sunshield. Now the telescope starts to deploy. So the secondary mirror support structure comes down, and then there's a radiator on the back side of the telescope that helps with detector cooling, and then one side and then the other. The primary mirror itself is kind of like a drop leaf table folded up, and then we unfold it. So that's the deployment sequence. That everything you just saw takes the first 2 weeks of the mission. It's all commanded from the ground except for that solar array deployment, which happens at about 30 minutes after launch, a few minutes after we separate from the launch vehicle. I mentioned L2 is kind of the Goldilocks position. This is a diagram of it in any. Whoops, let me back up. Where am I going? Sorry. Okay, in any 3-body gravitational problem, 2 massive bodies and then a 3rd insignificant body, there are 5 solutions to sort of metastable points. They're called the Lagrange points. There's L1, L2, and L3 are metastable. They're kind of they're not garbage collection points. They're kind of saddle shaped in, if you can visualize gravity gradient. But you can, it's not too hard to put something out there and with a little bit of active maintenance kind of orbit around those points. L4 and L5 are garbage collection points. They are gravity wells, and there's actually some objects hanging out those two places. Jupiter, the Sun Jupiter Lagrange point 4 and 5 are pretty big gravity wells because Jupiter's so big, and there are lots of asteroids and comets stuck in those locations, and they're called the Greek and Trojan asteroids. And NASA actually has a mission called Lucy that's going to go there and explore them, which is really cool. Earth has a small number of things at L4 and L5, but L2 is a great place for an infrared observatory because you can see that you can always have the sun, moon, and Earth on one side of your sunshade, and you can have your telescope in the shade of this big sun shield. And because the sun shield is oversized, we can actually pitch through 50 degrees and roll through 5 degrees side to side and yaw through 360. So we have this almost 2 pi steradian sized instantaneous field of regard. And over the course of 6 months, you've been able to access any point in the entire sky as we rotate around the sun. So great place to go. There are some other spacecraft at orbiting L2, like the Herschel and Planck missions. WMAP, a cosmic microwave background satellite, is there. It's a nice place to go. And L1 is where we, by the way, is where we put a lot of solar observing satellites, because they can just stare at the sun on one side and have their antenna pointing back at the Earth and in contact all the time with the Earth on the other. But yeah, L2 is a great place for something like this. And it's about 1 million miles away, 1.5 million kilometers away. It's not too hard to get to. So what does our orbit look like? This is kind of a cool graphic. If you're an observer from outside the solar system or above the plane of the solar system, this is our loop around L2. So we're about 1% farther away from the sun than the Earth is, but we stay with it. And we go in this loop. So every 6 months we have this loop. And the only complaint I have about this graphic is the Earth happens to subtend 0.5 degree of arc from L2. So it appears to be the same size as the sun, just like we have this lucky accident that we're alive today, that the moon happens to subtend 0.5 degree, just like the sun, and we get these beautiful eclipses. So the Earth from Webb's perspective will look the same size as the sun, but we purposely don't have eclipses because we want to always keep our solar array in sunshine and powered. And of course, we want to maintain thermal stability by having our attitude always, this orientation towards the sun, so that we minimize thermal changes that can warp the optics. Okay, so now some pictures of hardware, some of which are from many, many years ago. This is the primary mirror is made of 18 segments made out of beryllium and coated in gold. And each segment, you can see how big they are. Each segment is pretty lightweight. It's made of beryllium powder that was fused under intense pressure. Really uniform spherical powders, microscopic powder. That way we control the grain structure of the beryllium. This beryllium, if you tried to forecast it, it has a crazy grain structure, and it's very unpredictable in its shape. And if you take it through thermal cycles, it will change shape differently every time. So we wanted to use beryllium because it's stiff and it stops changing shape with temperature below 100 Kelvin. But by fusing it out of very uniform sized microspheres, we could control the grain structure, and we have very repeatable optics because we tested them many times and cycled them many times thermally on the ground, and we needed to know that they get to the right shape at temperature. And the first time we polished them and then took them cold, we measured what they looked like cold, and we used that to make a hit map for polishing off the high spots that exist at cold temperature when we go back to warm. So that's that whole make them perfectly wrong at room temperature, so exactly correct at operating temperature. And but we'll have to phase all of these 18 segments together to act as one mirror. We're going to be diffraction limited at 2 microns, so we're our total wavefront error for the mirrors working as one big primary, all the surfaces of the other mirrors. It's a 3-mirror anastigmat, by the way. And then all the mirrors, all the optics that are inside each instrument, when you add up the total end-to-end optical error from alignments and figure errors, it has to be less than 1/14 the wavelength of 2 microns, because that's where you become dominated by diffraction, and you're not limited by the imperfection in your alignments and your figures. So very nice optics. They have to be very precisely aligned. Each segment is movable in all 6 degrees of spatial freedom, and we have what we call a 7th degree of freedom, which is a force actuator in the middle of the mirrors that we can warp the mirror ever so slightly so that we can match the radii of curvature to a fraction of a millimeter, which we need that to as part of the total error budget of 150 nanometers for the entire optical system, including instruments. And we coat them in gold for infrared reflectivity. So, of course, gold looks gold to us because we see visible light with our eyes, and gold reflects blue light poorly, but red light very well. So it looks like gold. And if you extend its reflectivity into the infrared, it's superior to aluminum and silver, which of course are popular for visible light and ultraviolet telescopes. But so gold is great for what we're using here on the observatory. We tested each segment individually. This is some of them in a chamber down at Marshall Space Flight Center, where we tested them as individual segments. Here's what the secondary looks like, and it's kind of a cool picture because you can see the technician on a diving board above the primary mirror looking back up at the secondary and taking the photograph. The secondary is about 2 feet in diameter, and it's the one convex mirror in the system. And as I mentioned, it's a 3-mirror anastigmat. So right next to that in the middle of this image, right next to the photographer, you see the there's an entrance aperture there for what we call the aft optics subassembly, and there's a tertiary mirror there. It's the last powered mirror, but now the light's going the wrong way because it's your 3rd mirror. It's sending it back towards the secondary. So there's one more mirror, which is flat, and it's called the fine steering mirror, and it has an aperture mask on it that basically baffles all the light outside of the primary, this honeycomb edge of the primary. And we can tip and tilt that fast steering mirror at up to 100 hertz, and we use that to null out any final really tiny vibrations that would make the line of sight jump around. And we can also use the fine steering mirror for very fine pointing changes without having to move the whole observatory. So we can do dithers with the fine steering mirror. Here's the telescope as it was back in 2017. It doesn't have the sun shield and the spacecraft attached to it. We tested the cold half of the observatory. So all the instruments and the flight optics as a system, we put it into a relic of the Apollo era that we upgraded to be the world's finest cryogenic optical test facility. The vacuum chamber that's 9 stories tall and 6 stories wide and 6 stories in diameter. It's called Chamber A. It lives down at Johnson Space Center. And you can see people in this image. I mean, this is huge. We tested for 100 days straight at very, very cold temperatures. We got the inner walls of the chamber cool with by running liquid nitrogen through an outer shroud and running a closed cycle helium refrigerator for an inner shroud that could get to 11 Kelvin. And we were able to get the telescope down to survival temperatures of like 20 Kelvin and have this thing think it was operating in space behind a sun-shielded L2. And we, it was a 100-day test, and Hurricane Harvey happened right in the middle of it. And thank goodness we did so much planning and upgrading of the facility and did a lot of thinking about, well, what if we have a once in 500-year hurricane? What are we going to do? All that planning came in really handy because we managed to get through the test without losing any time or having to stop. It was hell on the test team because the toilets in their hotels weren't working, and it was really hard to get to and from work. And a lot of people stayed at the Space Center for days on cots because they really had nowhere to go. And we're doing the 24-hour test for 100 days, you know, with 3 shifts. And yeah, it was really something, but we pulled it off, and it was an amazing test. And this is what it was like going into the chamber. So, and this is what that chamber setup looks like. We, rather than building a conjugate telescope, we're having one giant autocollimating flat and then having sources at the detector focal planes. We actually put intermediate sources at the intermediate focus, the Cassegrain focus of the telescope. So it's not fully corrected. It hasn't gone through the tertiary mirror yet, but we put artificial sources using fibers to feed upward and downward light, and using 3 autocollimating flats, sample all the segments of the primary mirror, phase them, show that we could phase them to act as one surface, verify its figure. We used all the tooling we used here had nothing to do with the manufacture of the mirror. That was a lesson learned from Hubble. Don't use the same tools to test your mirror that you use to make it, because if you set up one of those tools wrong, and you use the same tool, you're gonna get a false positive. And that's exactly what happened with Hubble. Here we all this equipment to measure and verify the telescope was, and that the instruments and telescope together all work and are aligned correctly, and we can phase them, was done with means and tools independent of the manufacturer. We had a high-speed interferometer at the top of the chamber, feeding light to the system. The artificial stars we use for verification, like I said before. And this was quite the test, many, many years in the planning, and pulled it off. To move something like Webb, you got to build a really big container for it. This is our shipping container. So we've shipped the telescope like to Johnson, and then from Johnson to California to meet up with the Sunshield and spacecraft bus that were being manufactured and tested separately. We had to ship telescope in this big container, and we made this container a little bit taller to hold the entire observatory and send it on a ship down to its launch site in French Guiana just a few months ago. Final assembly and stowing. This is a view from inside the clean room with the telescope stowed, and the Sunshield partially stowed. It's just a really pretty shot. It was a very laborious process to test the deployments, and we did it multiple times because that's where so much of the risk that lies ahead of us with this machine is knowing that it will deploy correctly. There are 178 release devices that all have to work. There's almost a quarter mile of cabling that pulls the Sunshield taut. There are hundreds of motors, pulleys, and stem drives and sensors that are governing this whole thing. And because cables and Sunshield membranes are non-rigid floppy things, controlling them in zero gravity is a problem. You don't have to worry about things like the wings and the tripod coming down. They're rigid structures. They're easy to control. But controlling these floppy things meant we had to use a whole hundreds of different little elastic clips and devices that to control them deterministically as things are unfolding and as we're commanding it from the ground over a 2-week period. And testing that on the ground was quite the challenge. And so every time we deployed this thing and we had to stow it up again to test it again, it was almost like reassembly, very workmanship intensive, very strict checks and controls on it, and it was quite tedious, but very well controlled and understood, and we were able to do it successfully, but it did take a long time. So it really is an amazing machine when it comes to engineering, so that we can get it up into space, deployed and doing science. So I'll just end with there's a quote, my own quote from the article I wrote in November Sky and Telescope. Webb really is a marvelous machine. It's a remarkable achievement full of scientific potential and promise. It's been built to explore the frontiers of cosmology and astronomy, from observing the end of the cosmic dark ages to sniffing the atmospheres of exoplanets around nearby stars to perhaps detecting the chemistry that makes life possible as we know it. But its greatest discoveries will likely be answers to questions that have yet to be asked or imagined. And for me personally, that's the most exciting thing. Whenever we've created a new tool and looked at nature with it, we always discovered amazing things and been surprised. Ever since Galileo turned his crappy little telescope at the heavens, it's always been like this. So this machine is going to be truly amazing and produce amazing science that will rewrite textbooks. And it's pretty exciting to have been a part of it. And I hope you will enjoy its results. And maybe some of you will be proposers for observations. So that's all I have about Webb, and I'm happy to have a discussion, answer questions, however you want to go from here.
All right. Thank you so much, Paul. Do we want to give him a first round of applause? Yeah, let's do that. All right. So, Paul, you can stop sharing your screen for a moment, and so we can see you up here on the screen.
Sure.
And I will pass around microphones to folks in here. I see a few hands have been raised to ask some questions. I'll start with
This
Jeff.
is the guy that was talking. This guy.
Oh, okay. There you go. All right. I'm going to spotlight you up there, Paul. And Jeff Bryant has our first question. Go for it, Jeff.
Okay, you can hear me? Yep.
Yes, sir.
I have kind of two questions. One
Yes.
is considering that this has to be deployed, kind of reminds me of Galileo and the problem they had with deploying the antenna on Galileo that stuck.
Yes.
Did we learn anything from Galileo that helped us in this case concerning deployment, or is it a totally different setup? And then second, my question was, things like the infrared astronomical satellite that went up in the 80s, or maybe it was 70s, I think it was 80s. It ran out of fuel and then couldn't operate anymore. What's the lifetime for James Webb if it has to operate that cold? It's got to be artificially cooled to do that. So does it have liquid helium that will eventually evaporate and then it won't be able to operate that cool anymore? Anyway, those are my two questions.
Good question. So the first one, yeah, Galileo, yes, definitely lesson learned from any deployment. That was certainly one. You know, that had thermal aspects to it and friction aspects, and how it was tested on the ground versus you know, and what was learned and not learned. So that's part of why lessons learned from that we applied basically, you know, us doing many deployments and putting our deployment mechanisms themselves through thermal extremes to make sure they would work. And it also affected the design, so we made sure the design had a lot of margin and redundancy in it. Now that said, there are single point failures. Those membrane release devices that I mentioned. There's 178 release devices on the observatory total for all the deployments, and 107 of those are just to pin the membranes down in a stowed condition for launch, and those all have to work. And we spent a lot of time and effort to make sure that the workmanship on those was good, and that we have evidence that they're all going to work, and that they have a lot of margins, so that we have we can go through contingencies. So yeah, we learned from Galileo. We've learned from a lot of missions that have had major deployments, and hopefully we learn them well, and we'll have a deployable system. We have evidence that says we'll be okay, but nothing's without risk, and space is a very humbling business. So I know that we'll all breathe a partially exhale after the first 2 weeks of the mission, and our deployment should be done by then. Total commissioning is 6 months long, so there's a long time for cool down, settle out, equilibrate thermally, line the mirrors, calibrate all science instruments before we can do science ops 6 months after launch. But yeah, sigh of relief after the first 2 weeks for sure. And then the second question, yeah, we're mostly passively cooled. Just by being in the shade of that 5-layer sun shield, we attenuate over 200 kilowatts of solar insolation down to a fraction of a watt. And then by managing conducted heat and what little heat, say, the detectors themselves generate, we can cool passively simply by being in the shade. We will get to temperatures down into the 20s of Kelvin for the coldest parts of the telescope, merely by being in the shade and of this 5-layer sun shield and being at the L2 location. I did mention the mid-infrared instrument. It uses arsenic doped silicon detectors, and they need to be below 7 Kelvin to work, so that they're not just giving you noise. And so for that one instrument, for its detector modules, we have a 3-stage cryocooler, and the cooler compressors live in the spacecraft bus on the sunny side of the observatory, and we pump cold helium gas through tiny little stainless steel gold-coated tubes to those detectors, and we chill them to as low as 5.2 Kelvin, but they kind of want to operate best at about 6.2 or 6. So the only active cooling we have is a closed refrigerator that should last quite a while. We don't have consumable cryogen like IRAS did, or like Spitzer did, where they basically had big helium dewars, big thermos bottles full of liquid helium that slowly dissipated. Our passive cooling and our closed cycle helium cooler for the one set of detectors for the longer wavelength instrument. We don't have any consumable for keeping cold. The only consumable we have actually is rocket fuel. We're at a metastable point. We need a little bit of fuel for 2 things. Orbital maintenance, because it's not a stable place. Takes a little bit of squirting of thrusters every couple of weeks to maintain our orbit. We should have enough fuel for well over 10 years, assuming we get a good nominal ride from the Ariane rocket. And we also need fuel to dump momentum, because we use spinning reaction wheels to orient the spacecraft and turn it the same way Hubble does attitude changes. It can point with reaction wheels, but Hubble can dump its momentum by reacting against the Earth's magnetic field. It has these big electromagnetic torquer bars in the side of its light baffle, and we can just run current through those and push against the Earth's magnetic field and dump our momentum of the wheels, get them, spin them back down to medium range. But Webb's out in the breeze, so to speak. We have to push against something, so we use rocket fuel to do that. So that's our one consumable, is rocket fuel. But we don't have consumable cryogen. We get cold passively, and for the one thing that has to get really cold, you can't get cold by passive means alone. We have a little refrigerator to do that. So sorry for the long answer, but hopefully that answers your question.
We're going to have Sarah Lyon ask her question next, and then we'll go to Art Olson over here. So
it's a really simple question, Paul. I was just wondering, what is the flight time? How long from the launch to get to L2? What does that take?
It's about a month. So on day 29, we'll do our third mid-course correction. We call it mid-course correction 2 because we have 1A, 1B, and 2, but it's our third little burn. It's a small one. That puts us into our preferred loop around L2, and take about 29 days. But it takes less than 3 days to blow past the moon's orbit, which is a quarter of the way there. So you can imagine what we're doing is we're in powered flight for the first 26 minutes on the Ariane rocket, and we've gone about 10,000 kilometers. And so but we're climbing to a top of a hill gravitationally. So, and we want to stay at the top of this hill. And so it's kind of like pedaling a bike when you're on the first part of the hill, and you're pedaling as hard and as fast as you can for the 26 minutes. And then the next 29 days, you pedal just enough so that you coast and just stop perfectly at the top. So you go much faster at the beginning, and then you slow down rapidly. Like I said, in 1/10 the time it takes to get there, we'll be 1/4 of the way there. But yes, 29 days to get into this big looping orbit around L2. And the first 2 weeks, the first half of that journey is when we're doing all our major deployments.
Correlating to that, when do they project the launch to be?
Well, our launch readiness date right now is December 18th.
Okay.
That's our first launch opportunity. We're working really hard to meet that, but that's our first opportunity. And we launch in local morning. That's so that the sun angles as we're leaving and heading towards L2. The sun has only a grazing incidence to the stowed observatory because the mirrors are exposed. So we want the sun at grazing angles so things don't get too hot. And that means launching in the morning. And we have about a 30 to 35 minute launch window each morning. So our first opportunity is at 9:20 in the morning local time, or 7:20 Eastern time, or 6:20 Central time on December 28th.
Thanks very much, Paul. Appreciate your presentation. It's excellent.
Sure. Welcome.
go ahead. You got it.
There it is. Okay. Wonderful talk. Yeah, I love the detail. This is the kind of stuff that you don't read, you know, this is great. You said, I think earlier, that one of the secondary mirrors has a mask on the outside. Does that limit the actual diameter of the primary to the smallest diameter of that hexagonal edge?
It barely eats up any of the actual area of the primary mirror. The mask it looks just like the jagged edge of the
oh, I see. So it's not round. I just wondered if there was a reason for it to be round. I see. Yeah, it's not round.
Yeah, it looks just like the outer edge of the primary. It's on the fine steering mirror, which is where we happen to be re-imaging the primary mirror. So it's re-imaging the entrance pupil on this flat mirror, and that flat mirror is maybe this. Here we go. The camera. It's about this big, and that mask makes sure that any light coming from, say, stars behind the primary mirror, but to get in the entrance cone of the secondary mirror, they can't because of this mask.
Right.
Yeah.
Good. And another one is just sort of a curiosity question. Did someone calculate what the probability of success would be?
Yes.
I'm sure it's a high number, but is that something that can be shared?
No, it's a high number, and I'm embarrassed to say I don't know exactly what it is. It's a high number, but that meant all our little bits and pieces had to be really high because they multiply all together, right? So I don't remember the exact numbers, but it is high. But yeah, it means all those little release devices have to be more than 3 nines to, so when we add everything up, multiply everything, we're down in the 90% success rate region when you calculate it.
Good. Well, we all wish you the best of luck, of course.
Thank you.
Thanks.
Your
Mike,
tax
go ahead
dollars
with
work.
yeah, definitely. Mike, go ahead with your question, please.
I'm trying to unmute. Can you hear me?
Yes, we
Yes,
can.
yes, hi.
Okay, great. Actually, this is kind of along the lines of what Art asked about. I was wondering what kind of diffraction effects you're going to see from the sharp corners and the straight edges of the primary.
Yes, great question. So it is a little bit of a complicated point spread function, but because of those edges and gaps, there's like 5 millimeter gaps between the segments, and you've got the toothy outline of the. So it's a little bit of a complicated point spread function, certainly more than a perfectly circular, perfectly filled aperture, but it's still a pretty nice point spread function. Like I said, it can be diffraction limited at 2 microns, and it's really well characterized and understood. Scientists spend a lot of time figuring out how they, knowing the point spread function and accounting for that when they're going to analyze their data. I should have pictures of what that looks like, but it's a pretty one, but it's not your perfect airy disk, because it's not a perfectly circular aperture.
Yeah, but it won't limit the ability of imaging or anything. So.
No.
Okay, just curious. Thank you.
Sure.
Folks, do we have any other questions for Paul here?
I just got one quick question. So you're gonna it's gonna avoid all that extra space junk that's out there now when they launch it?
Yes. Yeah. Yes. L2 is a pretty clean place, actually. Most space junk. Well, first of all, L2, because it's metastable, not a gravity well. It's not collecting rocks. Other missions that have been there and are there give us some measurement of what the micrometeoroid environment's like, and it's pretty clean. And most space junk is in specific, inclinations and altitudes, specific orbits or in low Earth orbit. And a lot of it's still left over from the space race between the Americans and the Soviets, right? So, we're going to a place that's pretty clean, and we're getting out of the dirty neighborhood quickly. So, but we have we are going to get little tiny pinholes over time because there are micrometeoroids out there. We do know the environment, and you've got UV exposure over time on those sunshield membranes. So we know we've built that into the margin in the design so that we know things will last a long time, even as they degrade with just the natural environment.
All right. Any other questions for Paul Geithner here?
Ask him if he knows the current health of Hubble.
Jim Weimer wants to know if you know the current health of the Hubble Space Telescope.
It's good. I mean, we had a scare earlier this year when the science instrument command and data handling system had a failure. I forget the details of it, and we were able to switch sides on that, which is kind of a big deal when you switch sides, and it's fine. So it's working pretty nominally right now. I've been paying so much attention to Webb, I'm not sure, how many of the gyros are working and how many of the reaction wheels are working, and if all the modes of all the instruments are fine, but it's still working. It still gets, I think, 5 times every time I call a cycle. Observations are solicited annually, so they call it cycle whatever for however many years. So I guess it's cycle 21 or something we're up to now, because it was launched in 1990, and So proposals are solicited every year for the next year, and they get selected in a double-blind process and on merit, and then observations get coded and loaded up on like at least on Webb, it'll be a week, very similar on a weekly basis. We'll load up a whole week's worth of observations that the onboard computer will execute, and it still gets, I think, 5 times more proposals than there are time to execute. And cycle 1 got proposals all got selected for Webb a few months ago, and it was a similar, like 5 times as many proposals came in as there's time to execute for the first year. So as far as I know, Hubble is working fine right now, but I don't recall exactly, how much of what redundant systems are all good and all that, but it's still working. And we stopped servicing it, and what was it, 2009 or 2011 was the last visit, the 5th visit to Hubble. I worked on the first 2. The corrective optics I worked on are in the National Air and Space Museum today, because we've replaced all the instruments that it corrected the primary mirror error for. And so we removed it, I think, in 2009, and it's sitting in the Air and Space Museum, which is really cool because I hadn't seen it in a long time until it got back to Earth, and it's there. I think everything's working pretty well on Hubble, and knock on wood, hopefully it'll keep working for a long time. It's certainly working longer than it was ever intended, but it passes senior review every 5 years to keep operating because it's still a productive observatory.
All right, folks. You have any other questions for Paul? Oh, yes. Let me go ahead and hand you a microphone so you can ask it yourself. Here you go.
Hello. Thank you for great presentation. I have one question. So if something goes wrong with the instrument, then will there be any rescue plan? Like, for example, thanks.
That's a great question. There's no plan B. Actually, those were trades we looked at very early in the program. Was should we make this thing serviceable? Should we depend on servicing? We figured depending on servicing was a mistake for something that we're sending to L2, and a capability for which we couldn't foresee whether it would be in place or not. Moreover, it's an infrared observatory, so parts of it are at cryogenic temperatures. Good luck servicing that unless you warm it up. And I don't know how you do that without ruining it. So we weighed the costs and the risks and unknowns looking into the far future, and we said, we're not going to depend on servicing, and actually it's pretty hard to make it serviceable. So let's design it like almost every spacecraft is designed. Let's design it so it works. Now, because Space Station and Hubble are the oddballs where they were designed to be serviced and assembled, but satellites we depend on every day for just our ordinary lives. We build them to last a long time and not require servicing. Now, if you could service Webb, sure, it'd be great because detector technology improves all the time, and if you can stick new instruments on it, the optics don't really go bad. It takes a long time for them to go bad. So if you could replace the instruments every now and then, that'd be great. But the cryogenic nature of it and the cost and the risk and the ability to make it serviceable and still thermally work was just too high a hill to climb, and probably never would have gotten the thing off the ground if we had done that. So no, it's not serviceable. And even if we had the capability to go to L2 with robots or people now, it really wouldn't make sense. Now, there's one thing we can do to service it, and if somebody wants to do that, more power to them. But we've made it easy to refuel. As I mentioned, the one thing that is consumable on this spacecraft that's guaranteed to limit its lifetime is fuel. It needs fuel for momentum management and for orbit maintenance. So if somebody we've made it a cooperative target, and we made it simple for somebody to go and get a hold of it by its standard launch interface ring, unscrew the fuel and, you know, the gas caps, so to speak, and put more hydrazine and nitrogen tetroxide in it, if they can figure that out. But we're not depending on it. But if all the if all the electronics and mechanisms in the instruments in the spacecraft that fly the thing are still working in, you know, 20 years, which is a tall order. But hey, if they're still working and the observatory is still scientifically productive, but it's running low on fuel, and somebody goes, yeah, let's go robotically stick more fuel on it, they could, and that'd be really cool. So that's one thing that actually is serviceable, but we didn't plan on servicing. Sorry for the long answer, but it's a great question. We get that question a lot, and we thought about it a lot when we architected this thing many years ago. So appreciate the question.
Thank you very much.
Any other questions, folks? All right. Well, Paul, thank you so much for joining us. We really appreciate that you were here. Let's give him another round of applause.
Thank you so much.
Right.
Thank you.
Yeah, and I'll mention to folks here that Heidi, through the Illinois Space Grant Consortium over at the Department of Aerospace Engineering at the University of Illinois, she's acquired a number of freebies that I have here in the dome. And you folks are welcome to grab some, take them with you if you're leaving. But we're going to use the remaining time here for the club business. All right. So, Jeff, usually you are the person who handles our elections, and I think we should probably start with that with the little time that we have here. So if you want to take the floor, I'm going to hand you. Yeah, Paul, thanks you again.
Thanks so much, Paul.
Yep.
Thank you,
Thank
Paul.
you.